We're going to start the remaining sections to finish chapter 2. So we start with section 2.4 on page 144, and it's about formulas and percents. So this is just going to be an application of what we learned from previous sections. So we're going to start using the techniques, the algebraic techniques that we use to solve equations. We're going to use them to work on formulas and later to find percents. So the first thing that we're going to do is we're going to work with formulas. So formulas are just equations with more than one variable. With more than one variable. So you're going to find a lot of letters in the formula. And you are familiar with formulas. You have used formulas before. So for example, you can find the area of a rectangle by using a formula. So you know that if you have this rectangle and this is the length, we use an L for length and a W for width. You can find the area and you're going to use a capital A for area just by multiplying L and W. So this is an equation. This is an equation in 3 variables, and this is also a formula. So we call this a formula. So we're going to start solving. We're going to start solving a formula for one of its variables. So this is on page 145 in your book, and this is just a technique. This is just a procedure that you need to learn very well because you have formulas used in different fields of science like physics, chemistry, biology, psychology, education. In many fields you use formulas. So the way that we solve a formula for one of these variables is that you just need to focus on the variable of interest, and then just apply the techniques to solve equations, to solve linear equations, to solve for the variable of interest is what we're gonna do. So this is just an application of the techniques that we learned from previous section. We're gonna start with example 1 on page 146. So here you're gonna solve the formula capital A equals L times W for W. So there are 3 variables, but the one that is going to be our variable of interest is going to be W. So there are 3 variables here, area, length, and width, but we care or we are interested in this variable. So we're gonna have this as our variable of interest. So the rest are going to be treated as numbers. Just imagine that they are numbers. So what is L with respect to W? L is the coefficient of W. That's L. It's just a number multiplying your variable, so it's the coefficient of W. How do you solve for W? How do you solve for W in this case. So how do you remove a coefficient? How do you remove a coefficient? So if you remember the properties that we learned on the previous sections, by applying the addition property, the multiplication property, then you know that you need the multiplication property to solve for W here because you need to remove the coefficient. So let's do it. So A equals LW. So I'm going to divide both sides of the equation by the coefficient. So that's the way that you remove the coefficient. So you remove the coefficient by dividing by the coefficient. The coefficient is L. So that's the way that you remove this coefficient here by dividing by L. So you're going to end up with A over L equals W. And that's the solution for this problem. So you wanted, or we wanted, to isolate W. When we know that we are solving for a variable, we are isolating the variable. That's the meaning of solving for. So we remove the coefficient in this case, so that's the answer. So you're gonna see that working with formulas is easier than working with the traditional equation because you don't need to do any computation. You just need to move the letters from one part of to the other part of the equation. So it's going to be easier to work on formulas. But this is very important that you understand what you are doing because otherwise it's going to be very hard to do it. So let's work on more examples now. So I have example 2. So example 2 is on page 146. So we're going to work on another formula. So we're going to solve the formula. And we have 2L plus 2W equals P for W. So this formula is also used in geometry to find perimeters of rectangles. So again, we're gonna solve for W. So one more time, W is our variable of interest. Variable of interest. So this is like a linear equation. This is my linear term, so I'm going to isolate the linear term first. So how do you isolate the linear term? So the way that we do it is just by applying the addition property. So we need to remove this 2L from here. So we're going to subtract 2L from both sides of this equation. So if you do that, we remove these pieces from here. So we get 2W, plus 2W is the same thing. And here you just need to write what is here vertically, you just write it horizontally because you cannot combine these things. So this is P minus 2L. Now we need to isolate the variable. So the last step is we're going to isolate the variable. How do we isolate the variable in this case? We apply the multiplication property, so we need to divide. I'm going to write this again here for you to see it. We need to divide by the coefficient. In this case, I'm going to divide by 2. So if I do this, I'm getting rid of this coefficient. So my final answer is going to be W equals P minus 2L over 2. And that's now the formula written in a way that you can find the width when you are given the perimeter and the length of a rectangle. So we have two more problems, and then you're going to have work to do. So this is going to be half of the section of section 2.4. So let's work on example. What is this example? We're on page 47. This is example 3. Example 3 on page 147. So now we have a problem. I want to show you the problem, the word problem. So it says the total price of an article purchased on a monthly deferred payment plan is described by the following formula. Capital T equals capital D plus PM. In this formula, capital T is the total price, capital D is the down payment, P is the amount of the monthly payment, and M is the number of payments. Solve the formula for P. So we're going to write the formula. So in other words, we're going to solve the formula capital T equals capital D plus PM. We're going to solve this formula for P. So again, our first step is identifying the variable of interest. So this is my variable of interest. So imagine that the rest are just numbers. So this is a number, another number, and this is another number. So we need to solve for P. So first step, so this is our linear term. M is now going to be like the coefficient of P. So you can write this, writing M first and P after to see it as a coefficient. So we're going to isolate the linear term first. So what is the linear term? This is the linear term. So you have T equals D plus, and again, my variable is P, so M is the coefficient. So I'm going to write MP instead of PM. So now you see it as a coefficient. And to isolate this term from the rest, you're going to need to move this number here. So you're going to subtract D from both sides of the equation. In that way, we're going to have MP on the right-hand side alone. That's my linear term. So you just write this operation horizontally. So you're going to write T minus D equals, then the capital D's vanish. And then you get just MP. The last step is that you're going to isolate the variable of interest. So we're going to isolate P. So the coefficient is M. So we need to divide by M, both sides of the equation. So in that way, we're going to free P. And we're going to get T minus D over M equals P. And that's the answer for this problem. So now we're going to solve one more problem, and then you have work to do. So let's work on the next problem. So we have example 4 now. Example 4 is also on page 147, and the directions are solve the formula W over 2 minus 3H equals 53. We're going to solve this formula for W. So that's the problem. So what is the variable of interest? This is my variable of interest. Imagine that this is the X. So this is the variable of interest. You need to keep track of this variable. So first thing, we have denominator. So we're going to start. This is my step 0, remember? We need to remove denominators to be able to isolate our variable of interest. So the denominator is 2, so we're going to multiply every term by 2, every term on both sides of the equation. So we multiply this by 2, we multiply this by 2, and we also multiply this by 2, because 2 is the denominator I want to get rid of. So by doing this, we remove these two pieces. Remember, the denominator goes away also at the same time with the factor that we are using to get rid of the denominator. So we're going to get W minus 2 times 3 is going to be 6H equals 2 times 53. It's just going to be 106. So now I need to isolate the linear term. So we're going to isolate the linear term, which is W. So I'm going to add 6H to both sides of the equation. So we're going to get W equals 106 plus 6H. We are removing these two from the scene. And then we end up getting the answer, so we don't need to isolate the variable, it's already isolated. So isolating the linear term also lead us to isolate the variable, so the answer is just W equals, you can write first 6H and then the constant term. That's a convention to write the terms in depending on the power of the variable. So this is the answer for this problem. So now you're going to have to solve some problems from the corresponding exercise set. So this is 2.4 exercise set on page 152. You're going to solve for the indicated variable. 52. So for the indicated variable. So we have problem 12. So you have the formula equals P equals C plus MC, and you're gonna solve for M is your variable. Then you have problem 20. The formula is A equals 1/2 A plus B, and you're gonna solve for B. In problem 26, you have AX plus BY equals C, and you're gonna solve for Y. In problem 20, you can rewrite this as a fraction, so you can have here A equals, and you can have just A plus B, because if you multiply 1 and A plus B, you're gonna get A plus B over 2. So that's another way to write problem 20. Then you're gonna need to get rid of the denominator, then solve for B. So I'm going to give you a couple of minutes to work on this, and then we're gonna continue with the same section. So I'll start collecting your classwork, because at the end you're gonna need to take screenshots of all your work to submit. We're gonna start the last part of section 2.4, talking about percents. It's on page 148, and we're gonna deal with the formula involving percent. It's a very important formula, and this is gonna be our first chance to start translating English problems, English word problems into algebra. So this is the sentence. This is an English sentence that says A is P% of B, and we're gonna write this by using a formula. So we're gonna start translating every piece of this English sentence into a formula. So A is going to be A, is going to be always the equal sign. So is the equal sign. P%. So we're going to write something like P% of is going to be the multiplication operator and B. So A is P% of P. And to simplify our computations, we're going to rewrite P% by in a fraction form. So we're going to write A is P% of B. So this is our formula to compute percents. Then, depending on what is our variable of interest, we're going to be able to solve by using the previous technique. So we're going to start solving some examples. We're going to solve 3 examples, and then you're going to have work to do. So let's start with example 5 on page example 5 on page 149. So let's see. I'm going to write the question. What number is 8% of 20? So that's example 5. What number is 8% of 20? So we're going to start translating this question into algebra. So what number is just x, because we don't know the number yet, is the equal sign. 8% is written as A over 100. Of is just the multiplication operator, and then 20. So we have now an equation that is the algebraic representation of this question written in English. So we're translating English into algebraic equations. So now we just need to solve this equation. We already have x on the left-hand side, so we only need to perform the indicated operation. So this is going to be x equals 8 times 20 over 100. You can use your calculator. You're going to get 160 over 100. So this is going to be 1.6. So now you know that x is 1.6. So the number, so this is x, is 1.6. So I'm translating back to English. So the number is 1.6. And you can also write this. So 1.6 is 8% of 20. Okay? So that's example 5. Let's work 2 more examples, and then you're gonna work on that too. So example 6 is on page 149 too, and the question is 4 is 25% of what number? So we're going to translate this equation. I'm sorry, we're going to translate this question into an algebraic equation. So 4 is just 4. Is the equal sign. 25% is 25 over 100. Of is just the multiplication operator, and what number is just x. So I have my equation now. Now I need to solve for x because this is different from the previous case. So now I need first, I'm going to remove the denominators. So we're going to apply the same techniques that we learned to solve linear equations. So because this is a linear equation, so the denominator I want to get rid of is 100. So I'm going to multiply by 100 both sides of the equation. So I'm multiplying both sides of the equation by 100. So I'm going to be able to remove this and this. So I'm going to get 400 on the left-hand side equals 25x. Then we're going to isolate the variable. So now we're going to remove coefficients. We're going to remove the coefficient. So how do you remove coefficients? You divide by the coefficient that you want to remove. So 25 is the coefficient. So I'm going to get 400 over 25 equals x because I'm going to get rid of these two. And what is 400 over 25? Use your calculator, you're going to find this is 16. So 16 is the number. So you can write 16 is the number. I'm translating back to English, algebra to English. So you can say also that 4, so 4 is 25% of 16. Okay, one more problem and you have work to do. So the last problem that we're going to solve for this session, from this section, is example 7. So we have here example 7 on page 150. So now the problem is 1.3 is what percent of 26? So that's example 7. So let's translate this question into an algebraic equation. So 1.3 is then what percent? Now we're going to write P over 100, that's the percent, of 26. So we have now this equation. We're going to remove the denominators first. So we're going to start multiplying by 100 both sides of the equation. So if we do that, we can get rid of these 100s here. So we're going to get 130 on the left-hand side, and we get 26 times P on the right-hand side. So P times 26 is the same as 26 times P. So we use right first the coefficient and this, then the variable. So we remove the coefficient. That's the last step to isolate my variable. So how do you do that? We divide by the coefficient. This eliminates 26. So we end up with 130 over 26 equals P. So you do this division and you're going to find that 5 equals P. So the percent is 5. So 5% is the answer. So 5% is the answer. So you can write that 1.3 is 5% of 26. So you're going to solve now some exercises from this section. 2.4 exercise set on page 152. I'm going to write the entire question. So what number is 8% of 300? Then we have what number is 60% of 90? Then 32 is A is 40% of what number? Then the next one is 32% of what number is 51.2. Then 36. 18 is what percent of 90? And finally, the last problem is what percent is, what percent of 7.5 is 0.6. So these are your problems to finish this section. So we have more problems ahead to conclude the lecture, but I'm going to give you 15 minutes to work on this, and once I would like you to turn in at least problem 30, problem 34, and the last two, 36 and 38. So work on these problems, and then we're going to continue with the lecture, with the next section. We're going to start section 2.5. This is a section that is going to be very important for you to start working on problems related to the real life world problems. So this is an introduction to problem solving. This is on page 156. This is just about translating English sentences into equations. So it's very important that you're gonna read carefully the examples that are provided in this table, table 2.1. So you need to check it in your book, this table. So there are many English phrases and the corresponding algebraic expression. So you can have, for example, expressions involving addition, like the sum of a number and 7 is x plus 7, 5 more than a number, or a number plus 5, or another way is a number increased by 6, or 6 added to a number. So there are many, many ways to indicate that you are dealing with an addition. So, and also with subtraction, there are a lot of sentences or phrases in this case, because remember the sentence is going to be completed when you use the verb, and the verb is going to be usually is, and the verb is going to correspond always with the equal sign. So you have here many ways to find subtractions. Then on the next page, we have multiplication phrases, we have division phrases, and other ways to indicate or to translate phrases into algebraic expressions. So you need to read this table very carefully, and we're gonna solve one problem, two problems, and then I'm going to give you an assignment where you're gonna need to translate a lot of sentences into equations. This is important. So, and the only way to do it is just solving as many exercises as possible. So this is then our section 2.5, page 156. And this is just, you need to translate. We're gonna translate an English sentence, into an equation. So that's the goal of this chapter. So again, read table 2.1 on page 156. I'm not going to copy the table. It's better if you read it in your book. So we're going to start with example 1. So example 1 on page 158. So I'm going to copy the problem. It says that 9 subtracted from 8 times a number is 39. So I try to write the sentence in one single row to be able to create the equation. So then the final part is find the number. So I'm going to write here, find the number. So we have 9 subtracted from 8 times a number is and 39. So we have several pieces of this sentence. So is 39 is just the equal sign and 39. And once you find the verb, you have the left-hand side and the right-hand side in the sentence. So the right-hand side is just 39 in this case. So now we need to be careful when we are dealing with subtraction, because when you are dealing with subtraction, many times you need to reverse the order. So 9 subtracted from is that you're going to have the symbol for subtraction, but 9 subtracted from is that 9 goes here, and 8 times a number, 8 times a number goes here. So be careful about the order when you are dealing with subtraction. So 9 goes here, and 8 times goes here. So this is the only case that you need to be very careful when you are dealing with differences, when you are dealing with subtraction. So read carefully. So then you just need to solve the equation. So the equation is just ax minus 9 equals 39. And you know the steps. So the first steps, you're gonna isolate the linear term. So to do that, you just add 9 to both sides of the equation. So you're gonna get ax equals 48. Then you're gonna isolate the variable. So you have ax equals 48. To isolate the variable, you remove the coefficient. So you divide by the coefficient both sides of the equation. So you end up with x equals 6. So 6 is the solution for this problem. So that's the solution for this problem. So now I'm going to give you 8 problems from the exercise set. I'm going to solve you just the first one to repeat this process. So we have 2.5 exercise set on page 165, and all the problems were written in just a single row to be able to do the translation from English to algebra. So a number increase, so a number increased by 60 is equal to 410. So you have the verb here is equal to 410. Then a number x increased by is addition 60. So we have the equation x plus 60 equals 410. X plus 60 equals 410. You just need to isolate the variable by subtracting 60 from both sides of the equation. So you're gonna get x equals 350. So this is the answer. So we're on the remaining problems and we're on all of them. So if you have questions, send me an email. Remember, take screenshots when you're gonna ask me something to see your work. So I'm going to project the problems so you can take screenshots now or you can copy the problems. I'm going to give you some time. You can pause the video to copy the problems. Those are the first 4 problems. Now I'm going to project 3 more problems. Then final problem. And then you're gonna have 10 more minutes to work on this, collect your work, because you're gonna need to take screenshots before, when we finish the lecture. We continue now with section 2.6. We're gonna cover this section very briefly. I only need you to be able to use formulas involving geometry problems. So this section is about problem solving in geometry. It's on page 168 and it's based mostly on formulas that you're gonna find in table 2.3 of your book. So you have here formulas for the square, rectangle, triangle, and trapezoid. And you just need to be careful about what information is given, what is the variable that represents every part of every geometric figure, and then just use the corresponding formula and solve for the variable of interest. So this is just an application, again, of formulas. So the formulas are here. You have formulas for areas. There are formulas for areas. There are formulas for perimeters. So I'm going to solve just one problem. I'm going to give you one more problem to solve. And then we're going to be able to finish the lecture with the next section, which is one important section. That's the reason I'm just covering this very briefly, just to complete the requirements in the syllabus. So let's work on that now. So I just copy for you to have in the notes that in table 2.3 you have the common formulas for perimeter and area, and these are the formulas for the first 3 geometric figures: squares, rectangles, and triangles. So this is an S, so this is important that you take care of your handwriting, because sometimes the little s can be mistaken by like a number 5. So we're gonna start with the problem that is also from the exercise set. So this is 2.6 exercise set on page 177. So I'm using a problem that is going to be similar to the one that you might find in your quiz or in your test. So this problem is about a swimming pool. There is a rectangular swimming pool that has a width of 25 feet and an area of 1250 square feet. What is the pool's length is the question. So you have here the pool diagram. So the area is just 1250 square feet. You know that the width is this one. That's the width, and that's 25 feet. And the length goes from here to here, and that's what we want to know. So we check our formula sheet, and we see that we have a formula for the area of this rectangle, which is A equals L times W. So you need to understand that you are dealing with a rectangle. So read carefully your problem. Then the next step, once you have the formula, you're gonna substitute the values. So you're gonna replace the variables with the variables with the values that are given. So we're given the area 1250. We are not given L, so we're gonna write L, and then we are given 25. So we multiply A by 25. So how do you solve for L? In this case, you know that the coefficient is 25, so you need to divide both the left-hand side and the right-hand side by 25. That is the coefficient. So that's the only thing that we need to do here. So we remove the coefficient by dividing by the coefficient. So we're gonna get that 1250 over 25 equals L. You can use your calculator. You're gonna find that the length is 55th. So 55th. So the important thing is that when you are dealing with word problems, you need to use the corresponding units to finish your solution. So it's not just solving the equation and finding the number, it's also using the corresponding units. In this case, we are talking about a length, and the measurement is in feet. So now you have one more problem to work on. That is going to be problem 8, very similar to the one that we just solved. So copy the problem, take 5 minutes or less to solve this problem. Draw a diagram. Sometimes diagrams are very helpful to find the solution of problems. So work on this problem. I'm going to give you 5 minutes, and then we're going to start with the last section for corresponding to this chapter, and also the last section for this lecture. And then you're going to be ready for the first exam and for the first, and you're going to be able to also be able to work on your homework too, quiz number 2. But yeah, your first test is coming soon. We're going to start the last section of chapter 2, section 2.7. That's a very important section. So once you know how to solve linear equations, it's not going to be hard for you to understand how to solve linear inequalities. So there are going to be techniques that we're going to use that we borrow from our linear equation solution techniques. And there are going to be minor changes, especially when we deal with negative coefficients or negative denominators. So this section is important. So we're going to spend some time trying to understand this section. So the first thing is that we're going to we're going to need to understand some English phrases like greater than and the corresponding inequality symbol. So anytime that you have a problem talking about the value being greater than another value, you're going to use this symbol. That's the symbol for greater than. If in addition to saying greater than, there is also the or equal to. So greater than or equal to, then you need to use this symbol, and this little line here is the equal sign embedded into the inequality symbol. And you can have the opposite, which is less than. Then you use this symbol. This is the symbol for less than. Or if you have less than or equal to, then you embed the equal sign into the inequality symbol. There are some problems where the terminology or the phrases are slightly different. So for example, sometimes they say something like at least. When they say something that at least is equivalent to greater than or equal to. Sometimes they say at most. At most is equivalent to less than or equal to. So what are the properties that we're going to use? So we're going to use some properties. I'm going to borrow some properties. Properties that we're going to use to solve linear inequalities. So we're going to use the addition property in the same way that we use the addition property when we solve linear equation. So now you have A greater than B. This is my inequality, my linear inequality. I can add a quantity or an expression to the left-hand side, and I need to do it to the right-hand side too. And then just write A plus C greater than B plus C. So nothing different from what we did with the linear equation. So the addition property works in the same way. So now what happens when you multiply both sides of an inequality? There is something that you need to be careful when you multiply a linear inequality. So you can apply the multiplication property, but if you multiply or divide by a negative number, then you need to reverse the direction of the inequality symbol. So this is important, because if you don't do this, your answer is going to be wrong. So let's see. If you have A greater than B, you multiply both sides of this equation by 3, which is a positive number, then you just get 3A greater than 3B, so nothing changes, so the direction goes to the right. So, but if you have A greater than B and you multiply both the left-hand side and the left-hand side by a negative number like -3, then you need to switch the inequality. You need to reverse the direction. So instead of being greater than, now it's going to be less than. So this is important. I'm going to emphasize this for you to see the difference with respect to the other case. So less than. So the answer is going to be negative 3A is less than negative 3B. So that's the only thing that you need to take into account. The rest, you apply the same techniques that you use for to solve linear equations. So one more thing. Now the solution is not going to be a single value. Most of the time, the solution is going to be a set of values, a lot of values. So most of the time, we need to provide a graphical representation of the solution, because sometimes it's better to understand the solution. So we're going to do some graphing. So we're going to graph linear inequalities in one variable by using the real number line. So remember, the real number line goes from -infinity to +infinity, and that's the line that we're going to use to graph our solutions for linear inequalities. So what are the things that we need to take care of? We need to find the boundary and the type of boundary. So most of the time, when you are graphing a solution, you're gonna divide the line in two parts or many other parts. So, but usually in two parts. So one part is gonna be the solution and the other part is not going to be the solution. So, and the line dividing those two parts is gonna be the boundary. So the boundary is gonna separate. So the boundary separates the solution region from the non-solution region. So that's the reason we need the number line. So we need to find the boundary. And also we need to find the type of boundary. So there are two types of boundaries. We're going to have open boundaries or closed boundaries. So the open boundaries are the ones that are related to these symbols, greater than or less than, and the closed boundaries are the ones that they incorporate also the equal sign. So what is the meaning of this? Is that when you have a closed boundary, you're going to use a dot, a full dot in your number line, and that means that the dot is part of the solution. So this is, the boundary is part of the solution. When you have an open boundary, then you're going to use an empty dot, and the meaning is that the boundary is not part of the solution. So you can write here, open boundaries are not part of the solution. Let me write this here. Open boundaries are not part of the solution, whereas closed boundaries are part of the solution. So that's what we need to take into account. So we need to find the boundary, and then we need to find the kind of boundary. So remember, we're going to use open dots for open boundaries and full dots, so completely filled dots for closed boundaries. So we're going to start solving some exercises dealing with graphing solutions, and then we're going to find the actual solutions, even any inequality. So we're going to start with example 1 on page 183. It's just we're gonna graph the solutions of each inequality. So we're gonna start with the first one. The first one is x is less than 3. So imagine that we find this. This is the last step when we are solving a linear inequality. So this is the solution. This is the algebraic or the analytical solution. We need the graphical solution to see this in a better way. So we're gonna use a number line. So we're gonna use a number line, and we need to understand these things. So the number 3 is gonna be the boundary. So I wrote this here and I didn't say it. So the numerical value after the inequality symbol is the boundary. So once you get the solution, of course. So this is the boundary. So 3 is the boundary, and the symbol indicates the kind of boundary. In this case, this is an open boundary. So we need to find number 3 in our number line. So let's say that number 3 is here. So, and this is positive infinity, negative infinity. So we need to draw an open dot, an open circle on 3, because the boundary is open. And then we're gonna highlight the region that makes this statement to be true. So we are looking for the values that are less than 3. So usually the inequality, the tip of the inequality points to the solution region. So this is pointing to the left. So we're gonna highlight, we're gonna draw an arrow pointing to the left, indicating that everything left to the number 3 is the solution region. So that's what we're gonna do here. So that's the solution region. Another thing that we're gonna do now, to take this example to explain that, we're gonna use also the interval notation. The interval notation is important. That's another way to express the solution of inequalities. So the interval notation starts with writing a parenthesis or a square bracket, depending on whether you have an open boundary or a closed boundary. You're gonna use parentheses for open boundaries. So the solution region goes from this number 3 to the left. So we're gonna use always a parenthesis for negative infinity. Always the negative infinity or positive infinity are open boundaries because we don't know the extension. Then we're gonna use a comma. That's my left boundary. For my solution is negative infinity. My right boundary is just number 3 and it's open. So that's the way that we represent this solution by using the interval notation. When you have closed boundaries, like in the next example, then we're going to use square brackets. So I'm going to work now the second part of example 1. So let's see. So we have now B is x is greater than or equal than -1. So now again, the boundary is at -1. The boundary is closed, so meaning that the boundary is part of the solution. So we're going to have our number line, positive infinity, negative infinity, 0. Now we look for -1. So -1 is here. So you can draw on top of the line, or you can draw above or below. Sometimes I prefer doing my drawings a little bit off from the line to prevent a lot of mess here. So -1 closed boundary is just a closed boundary, is just a dot that is filled. Then now the direction of the inequality points to the right, so I'm going to draw an arrow pointing to the right. So this is one end of my region. So this is the left boundary now, because now my right boundary is going to be positive infinity. So I'm going to have a parenthesis here, and I'm going to have a square bracket here with -1. So this is just -1, comma, infinity. So this is the interval notation, but see how I'm using the number line to also obtain the interval notation, because I'm just using the number line. I'm writing parentheses of square brackets at the boundaries, the boundary that is given here, and also the other boundary is just where the number line ends. In this case, ends at infinity. So that's what we do. That's the way that we represent inequalities. Let's work on the last part of this example. So now we're going to represent -1. There is no less than, it's just less than x, less than or equal than 3. So you don't take into account this, just less than only. So this is open boundary. And this is a closed boundary. And now we have the left boundary is -1 and the right boundary is 3. So you have here -1, you have 3, you have 0, positive infinity, negative infinity. So you have on the left an open boundary, so you have an empty dot. You have a closed boundary at 3. So you do this, and then you just draw a line here. So this is the solution region that goes from an open and ends into a closed boundary, and then you just write -1, comma, 3. So this is the interval notation. So that's example 1. Now we're going to start solving linear inequalities. And then you're going to have work to do. We're almost done with this chapter. I'm going to solve 1, 2, 3, 4 problems for you. And then you're going to be able to work on the exercise set. So I'm going to start, I'm going to start solving linear inequalities. So this part is very important. You're going to be tested on this in your first test and also in your corresponding quiz. So this is important, solving linear inequalities. So I'm going to highlight this. So these are notes that you need to check many times because this is equivalent to solving linear equations. So those 2 parts of this chapter are the ones that I expect you to work very well once you finish watching this this video. So we have example 3. Example 3 is on page 186. So let me see. So we're gonna solve. So the directions are solve and graph the solution set and graph the solution set on a number line. So I'm copying the entire direction in this case. In the coming problems, I'm just going to write solve and graph. You can understand that I'm talking about graphing the solution set on a number line. So the inequality is just x plus 3 less than 8. So that's the inequality. So how do we solve this? We need to isolate the variable. So that's what we do when we have equations. So we're gonna isolate the linear term in this case, but the linear term is also, we will isolate the linear term first because there is no coefficient, but the coefficient is 1, that's fine. So how do you isolate the linear term? So you subtract 3 from both sides of the inequality. We are subtracting. We are not multiplying, so don't change the direction of the inequality. So in this case, this addition or subtraction. In that case, we just follow the rules that we follow for equations. So 8 minus 3 is going to be 5. So adding negative numbers does not affect the direction of the inequality symbol. Please, this is a very important note because sometimes students, because they are adding negative 3, they switch the symbol. No, you do that only when you are multiplying or dividing by a negative number, but not when you are adding negative numbers. So the addition property doesn't affect the inequality symbol. So this is the solution. This is the analytical solution. So I just need to write, I need to get the graph. So I'm going to write negative infinity here, positive infinity here. This is the boundary, it's at 5. The symbol indicates to me that the solution region goes to the left. So and I need to use an open dot for this boundary because this is an open boundary and goes to the left. So that's the graph. So usually we should draw this on top of the line, but for you to understand, it's better if I do it apart from the line. But yeah, if you look at your book, you're gonna see that this arrow with this dot is on top of the line, but I cannot do that without making this very confusing. So that's the solution. Now the interval notation is gonna be just parentheses where negative infinity is, comma, then 5, and another parenthesis here because this is an open boundary. So this is the interval solution. So let's continue with 3 more problems, and then you're going to start practicing this by yourself. So let's work on the next example. So this is example 4. Example 4 on page 187. We're going to solve and graph. So now we have 4x minus 1 greater than or equal to 3x minus 6. So first step, we're gonna collect all the linear terms on one side of the inequality. So I'm going to move this 3x to the left-hand side. How? Subtracting from both sides of the inequality, subtracting 3x. So 4x minus 3x is going to be just 1x. I have this negative 1. Don't forget what is left. And then these two cancel, so I'm just going to get negative 6. So this is like solving an equation when you use the addition property. Now, we're going to isolate the linear term. Isolate the linear term. How do you do that? You just need to remove this negative 1 with that positive 1. So you're going to get 1x, which is just x, greater than or equal, and negative 6 plus 1 is going to be negative 5. So that's the analytical solution. Then we're going to use a graph, a real number line. So negative infinity, positive infinity. We find negative 5 here. This is a closed boundary. So we're going to use a dot. That inequality symbol points to the right, so that means that my solution goes in that way. This is valid, this idea that this points to the solution region, only when you have the variable on the left-hand side. So be careful when you have the variable on the left-hand side, then the inequality is pointing to the right region. So now you just need to change this arrow into an interval notation. So negative 5 is a closed boundary. Then we have a comma, and this ends at infinity. And we always use a parenthesis for the infinity. So now, example 5. Example 5. So again, this is analytical solution. This is the graphical solution. And this is the interval notation solution. So example 5 is on page 187. There are two parts. The first one is 1/3 of x is less than 5. So first we remove denominators. So how you multiply by 3 both sides of the inequality. I'm keeping the same direction because I'm multiplying by a positive number, so no need to switch the sign. So you just cancel here these 3 and these 3. So you end up with 1x, which is just x, less than 15. So now the graphical solution. So this is the analytical solution, The graphical solution is going to be just my number line. I have 15 here, there's an open, and goes to the left. So the interval notation is going to be 15, negative infinity, and open 2. So part B is just negative 3x less than 21. So first we remove coefficients to isolate the variable. We remove coefficients. We remove the coefficient. So the coefficient is negative 3. I need to divide by negative 3. So I'm going to have negative 3x divided by negative 3. I'm divided by a negative number, so I need immediately switch the sign, the inequality symbol. So 21 divided by negative 3. And then you just finish the computation. So you cancel these 2. So you get x greater than negative 7. This is analytical solution, then the graphical solution. Analytical solution. This is the graphical solution. And this is the interval notation. So we need the number line. So the number line is -7. So we're going to use an open dot, an empty dot that goes, and then a region that goes to the right. So the interval notation is going to be -7, comma, and we end at infinity. So that's example 5. So we have, I think, 2 more examples. No, just one more. You're gonna work on this. Perfect. Sounds good. So let's work on the last example. The last example is example 7. On page 189. So we're gonna solve and graph 7x plus 15 greater than or equal than 13x plus 51. So what we are going to do first is we're going to collect the linear terms on one side, usually the left-hand side. So we're going to subtract 13x. And again, this is an addition, so no need to change the direction of inequality. We are not multiplying, we are not dividing, we are just subtracting. We are adding a negative quantity. So 7x minus 13x is going to be -6x plus 15 greater than or equal than 51, because these two cancel. So now we're going to isolate the linear term now. I'm going to isolate the linear term by subtracting 15. Let's do that. And again, we are adding a negative number, so no need to change the direction of inequality. So you just get -6x greater than, in this case, 51 minus 15 is going to be 36. Now we're going to isolate the variable by removing the coefficient. How do you remove a coefficient? You divide by the coefficient. So we're going to divide this by -6. But now we are dividing by a negative number, so we need to switch the symbol because we are dividing by a negative number. So check this. Okay, we are dividing by a negative number, so we need to switch the symbol. So now we're gonna remove this -6 from here. So we're gonna end up with x less than or equal to -6. So this is the analytical solution. Then we just need to graph this. So we have negative infinity, positive infinity. We have -6 around here. This is a closed boundary, and the region goes to the left of this boundary. So from here you can just write negative infinity, comma, -6, and this is a closed boundary, so you require a square bracket to indicate the interval. This is a solution interval. And this is the graphical solution. So that's it for this chapter. So you just work, use 2 problems from this exercise set on page 195. So you're gonna solve and graph Problem 28 is just 2x plus 9 less than or equal than x plus 2. And problem 36 is going to be y plus 1/3 less than or equal than 3/4. So solve these two problems. I need you to turn into me these two problems. So you're going to take screenshots from this, from the solution of these problems from your work. And also you're going to incorporate the work that you performed throughout this lecture. Take screenshots, use an app that transforms these screenshots into a PDF file, and that's what you need to submit to get your points corresponding to classwork 2B. So that's it. That's the end of chapter 2. And we are ready for the test. So I'm going to prepare a video showing, it's going to be a review session. I'm going to collect some problems from the students, their questions. I'm going to prepare the video. If you have a problem to be solved, just send me the problem, the page, the number that is in the book, and I'm going to try to incorporate that into the lecture, into the review session. And then you're going to need to take your exam by using Proctorio. So don't forget checking how to use Proctorio. I'm going to give you information on how to do that. It's very easy. You just need a webcam. You need your laptop. You need your microphone. You cannot use your smartphone to take the exam. So because you need a laptop, that's the regulations set by the college when you use Proctorio. It's not hard. It's just for the integrity of the exam.